We are recording. I'll start with, so we start with significant figures. Those of you who took chemistry before or saw significant figures somewhere before, were you comfortable with it? Did you hate it? Did you have a hard time with it? No? Well, that's where we're going to start. So let me first say something like, nearly every time we have a value, pretty much every time we have a numerical value to deal with. Make sure this is still recording. And there's basically three components there. There's a numerical value, there's a unit, and I could just call this the label. Meaning 23.46 inches, it's 23.46, but 23.46 what? Feet, pounds, meters, what? Well, that's what this is. It tells you what the actual measurement is, what this number means. And then the label tells you what it's referring to. 23.46 inches, is that the height of my chair, or is it how long it is from my foot to my knee? No, it's a notebook, it's some notebook. So every time we have a numerical value, we're always going to have a unit that goes with it and a label that goes with it. To start with, I'm going to start us off just talking about that numerical value. Because significant figures don't really have anything to do with that stuff. It has to do with this part and what you do with it when you do the calculations. So let me start by this. Just about every number we deal with this semester is going to be coming from a measurement somewhere. So you can think of yourself as the writer of a number when you're the one doing the measurement. You make a measurement and you record it. If you were recording a measurement for this, this is the halfway point. So, and let's say I'm measuring this is just like a steel bar that I measure. It's at least 24 inches. It's not quite 25 inches. So the first thing I would write down is 24 for this. And I'm really looking here and going, okay, it's greater than 24, less than 25, that's 24. And then this splits up into 10 increments, the decimal system. This would be 1, 2, 3, 4, 5. Meaning if this bar was this long, I would be 0.1, 0.2, 0.3, 0.4. What should I put here? Somebody said 0.7. Because this line is the 0.7 line. But you always do this when you're making a measurement, and you'll do this mostly with a graduated cylinder for volume, and you'll be looking at it, and it looks very much like this. We probably have some exercises we do where we measure things with rulers and stuff. But most of the time in chemistry, the measurement you're reading is a graduated cylinder for volume. All right, so I can get another digit out of this, and that's really the whole point that I'm showing here. If you just picture between these two 10 increments, and you try to decide what number this would be, you are estimating, but your estimate's still going to be very good. So you always make that last estimate. The one thing that doesn't feel very scientific, but it still gives you a whole extra digit of precision here, and that's the goal. What would you put for that, for the next digit? 5. It does look like it's right in the middle. So 5 is fine. If you put 4, if I just randomly had everybody go, okay, what do you read there? Most people are probably going to have a 5. There will be a handful that's got a 4. Maybe somebody might say it's a 3, but no one's going to make this a 9 or a 1. You see what I'm saying? You're not going to use 9, 8, 7, 6. You can tell that's either halfway or a little below halfway maybe. So my point is, even though you're estimating, it's still a good estimate. You're probably within one digit if you're wrong at all. And that still gives us a whole extra digit to work with. We just usually say that's the most uncertain digit and the rest are certain. And this one's kind of uncertain. Because it's definitely more than 24 and less than 25, so that's correct. it's definitely between 0.7 and 0.8, so that's 100% correct. This is the only part we have a little bit of iffy judgment. All right, so let me do this, just to kind of drive home the point. If that was the length of my bar, I'm still going to say 24. And what's the next digit? Still a 7. And here's where these trailing, what we'll call trailing zeros, arise. Just the fact that it lines up with this line, we're not going to throw away this digit, but we're not going to put a 1 there, or a 2 there, or a 3 there. We're going to put a 0 there. Because it's kind of lined up right on the line. And we did make a judgment. We tried to judge where it is in between here, but we discovered that it was right here. That happens sometimes. So that's why we wrote a 0 here. And if it went all the way up to here, then we'd be changing it to an 8. This would be an 8 if it went all the way up to this one. But the point is this 0, if someone walked up to you and said, here's a number for you, have fun. There's a number, 24.7. You probably know this, that theoretically there's an infinite number of zeros all the way out to infinity. And truthfully, you could write an infinite amount of zeros to this side, infinity, but it doesn't change this number. So, okay, I've got this up. So let me get away from you being the writer of the number, and now you're the person who reads the number. So most of today, you're taking the role of a person reading the number. Someone else made the measurement, we trust that they did it correctly, and now you're looking at a number and you're trying to do something with that number. So starting with slide 1 here, number 1 on slide 1, all non-zero digits are significant. I should have done this. Let me go 24, 0.70. Notice that the more of these that we can actually measure, the more precise of a measurement we have. So this has 4 digits of precision. We also say significant figures, 4 digits of precision. A better instrument might come along and we might find, if we could zoom in really close and see really close, you might be able to get more digits out of it. So this is related to how many digits we have is related to how precise of a measurement we make. Okay, so let me, I keep forgetting where the eraser is. Stuck to the board. Now, that first directive on the first slide, number 1, all non-zero digits are significant. It's actually kind of obvious in a way. I purposely wrote these so there were no zeros, and now, right here at the beginning of the class, you can find out how to find the number of significant figures very easily. You just count the digits that you see. I mean, how many digits do you see here? 6, all 6 of them are significant figures. How many here? 3. All 3 of those are significant figures. This has 6, this has 4. It's very easy to decide how many significant digits you have if there's no zeros. It's the zeros that cause confusion. So realize right off the bat, something that doesn't have any zeros, you got that, you just count the digits that you see. Now, going to the next one, I think number 2 is the interior zeros. Let me do 3 and 4 first. Leading zeros. So number 3 on that list, leading zeros. First of all, here's some leading zeros. This is what we mean by leading zeros. The zeros that come from the left all the way up to when you get to your first non-zero number. And try to see that this is obvious too. Those, of course, are not going to be significant figures. In fact, I haven't gotten to why zeros are confusing in the first place. I see old gas pumps And there's some old alarm clocks that they're actually little cards that flip. And if you haven't used a digit over to the left yet, it just sits there at 0. So there are places in the world where you see zeros out to the left like this, but nobody ever writes those. If I ask you to go count something and it turns out there were 1,632 of them, and you wrote it down, you're probably not going to write any zeros out to the left. You would just feel weird doing it. So take care of number 3 on that list. That's kind of obvious too. Leading zeros, that is zeros coming from this way, those never count. And there's another case, 0, 0, 0, 0, 0.0000643. Even if you're coming from this side and you're going through a bunch of zeros, trying to get to your first non-zero digit, it's okay if you stumble over the decimal point. These still don't count. These still don't count. So if you start with zeros and you just keep going through zeros until you get to your first non-zero digit, that's where the significant figures start. And accept that it's kind of obvious. If that seems confusing, just realize these first 2 rules I mentioned, they're confusing because they're so obvious, I think. But just let it be obvious to you that those have nothing to do with the 4 digits of precision that somebody measured here. They never measured anything out here. So those are just throwaway. We usually don't write them anyway. I mean, it would be more natural for you to write these numbers like this. And this one, we usually draw the first 0 on this side of the decimal. I don't know why, but that's been a convention for a long time. That's probably the way you would see it if somebody measured it. The only time you see zeros written out to the left is in a chapter like this where they're trying to drive home this fact, and then you never see it again. Maybe you'll see this just because it locates the decimal. So these are all leading zeros. So rule 3 there, leading zeros never count. It's the trailing zeros that tends to trip people up. And I had one here. That's why I wanted to do that. I wanted to show you why sometimes there is a 0 on the right, what we call trailing zeros. Trailing zeros, they're on the right side of the decimal. There are technically an infinite number of zeros going out this way, but only this one was measured, and that's where this number is going to stop. Meaning the writer of this number, you're the reader of the number, the writer of this number, by putting this 0 here, they're telling you they did actually measure that. It just happened to be right on the line, but it's measured. They actually got that significant digit. You see what I'm saying? That's why I started with that example, just to show you how zeros arise on the right side. So this is 4 significant figures, what you're looking at there. These are significant, and this one is also, but nothing more. Because the writer of the number stopped there and put a 0 there. If that were a non-zero, it would just be obvious that it's a significant digit. But the fact that it's a 0 might confuse you. But those are significant, the ones on the right side of the decimal. Trailing zeros on the right side of the decimal. And you might even see numbers like, and there's like more than 1 0 in it. If the writer of the number put those zeros there, they count. This is 1, 2, 3, 4, 5 digits of precision, also known as significant figures, or sig figs, I say a lot. You with me so far? The other one that's kind of obvious is, I've always called them sandwich zeros. This, what calls them interior zeros. Interior zeros. But I think this will be obvious too. The significant digits, this is really kind of obvious if you think about it, they're always contiguous. It's not like you can have, yeah, that's significant, and then this one is not, but then the next one is. They're always together. They're always contiguous. So this 0 and this 0, they definitely count. They're literally part of the number. They're sandwiched in there, they definitely count. So it's leading zeros that don't count, and any zeros that are not written on the right side don't count. Interior zeros count, zeros on the end count, towards significant figures. That's the rules here. There's one weird rule. And then they mention it here at the bottom, very bottom of this page. Some textbooks put a decimal point after 1 or more trailing zeros. Okay. What they're getting at is this convention. You don't often see this, but in science, if someone wrote 2600 without a decimal, these two zeros do not count. They weren't measured. They're just kind of locating the decimal place. That's two significant figures right there. This one is showing four significant figures. The decimal indicates that these zeros just to the left count towards the number. That's the weird one. The book acts like it's rare, but it's not as rare as the book pretends it is. Some textbooks put a decimal point after it says something. We avoid that practice in this book. All other scientists use that convention, and all other books do, so we shouldn't really ignore it. Okay, significant figures. The next thing to discuss is we will frequently have some values that we're going to do calculations with, and we have to decide what we're doing with our answer. This is best done by example. I will. So number one on slide 2, the multiplication division rule. Pop up with some examples. I guess I'll do those. The examples that are on the slide. Okay. First, I'll do the multiplication division rule. Do this example. Okay. So this is the calculation I need to make. What you can do right at the beginning for the multiplication division rule is you look at how many significant figures are in your input values. So how many significant figures are here?
4.
There's 4. There's no leading zeros. There's no trailing zeros. There is one sandwiched in there. 1, 2, 3, 4. 4 significant figures. So this one's 4. How many here?
5.
That one has 5 significant figures. And this one?
2.
It's 2. All right. What we have to find is the smallest number we have up here. We have to round our answer to that. So this needs to be 2 significant figures. We can do that before you do a calculation. Okay, you of course get to use calculators in this class. I think you're going to be stuck using these that we keep laying out here. They're all attached to each other in pairs. So you might want to get used to using those. But I'm just going to use my calculator. So you don't have to do it now. Just realize that's what you'll be using for the test. But okay, so the way I do this is I would go 1.052 times 12.054 times 0.53. All right, my calculator says So I just wrote down everything my calculator gave me. I think it's the best way to understand this. I hope that shows up. But this is the way I do it. I write down everything my calculator gives me. And then I look up here and I go, okay, it's 2. So it's those 2 places that I'm going to preserve my calculation. But you do look one more digit out at that number, and you decide whether you have to round that 7. But you guys know the rounding rules, right? If it's 5 or higher, you round it up. If it's 4 or lower, you don't. So the 2 doesn't round to 7. So there, we're done. That's our answer. We just use the multiplication division rule to decide where to round our answer. It can only be as accurate or precise as the input values were precise. And our least precise input value was this one, 2, so we had to round that one to 2. That's the multiplication division. You guys good?
Yes, sir.
So it can only be two significant numbers as the answer?
Yeah, the answer you would report for this, to get it correct, it would have to be 6.7. If you had 6.72 as your final answer, you did it,
Okay.
because you rounded to 3.
So you only always use the last significant number?
The least,
The least.
yeah, the one with the least significant digits.
Okay.
You put your answer in that. It's like saying your answer can't be any more precise than the input value. I mean, that number, we sure as heck didn't have that kind of precision in any of these measurements. So we certainly don't have to do our answer. To do it properly, whichever one of these has the least amount of precision, your answer has to have that kind of precision. Okay, that's the multiplication division. Addition subtraction rule is a little bit different. All this time I'm talking about significant digits. Actually, the significant digits don't come up when we do those. Where's my picture? What do they have here? Let's do that one. Oh, let me just make one up. You guys? Addition, subtraction. Okay. Again, we can look at the input values and determine something about our final answer. But this time, we don't look at the significant figures. We look at how many are after the decimal. This one has 2 after the decimal. This one has 3. This one has 1. That tells us 1 after the decimal is where we have to round back our answer. All right, so let's see what my calculator does with this. 23.41 plus 4.491 minus 10.1. My calculator says 17.80. And now we have to fix it up for its digits. This has to be the end of the digits, so this part has to go away. So it ends up being these 3 digits. So it ends up being 3 significant figures. The 0 does not round to 8. So final answer, 17.8. This had this much precision after the decimal. This one had this much precision after the decimal. This one only had 1 precision after the decimal. So we had to round our answers back to that position. Again, it's the least number, but it's the one that has the least number of digits after the decimal. That's the addition subtraction. As far as these notes on here, number 3 on slide 2, that's just telling you how to round. I think you already knew that. And number 4 here is discussing what do you do when you have a mixed situation, where you have a calculation that has some subtraction in it and some subtraction or addition in it, mixed with some multiplication or division. You do one other weird little thing. I'll do this one. Okay, so the combined says 6.78. So now we have multiple steps to go through. So of course, what you do first is you do the subtraction first. And again, you're gonna use the addition subtraction rule by going, there's 3 after the decimal here, 2 here. So 2 after the decimal is what that answer needs to be. Put this in my calculator, it gives me 5.489 minus 5.01. That's what my calculator says. Here's where things are different. I am going to underline right here because it's 2 after the decimal that's supposed to be. But I'm going to keep any extra digits I have here because it makes the calculation come out more accurate. If you start rounding things before you're done, it changes the outcome of the calculation. But I'm still going to put that underline here to remind me. All right. So that's what that came to. And now I can do the rest of this. And now I'm going to use the multiplication division. This one is 3 significant figures. This one is 4 significant figures. And this one should be 2, even though I've got 3 written here. That's why I put the underline there to tell me that that's really 2. But I am going to use any digits I have here to do this multiplication.
But you want to add the 2?
Well, if I had done this properly, at this point, I would have turned that 7 into an 8 and said, the answer to this is 0.48. But because I have more steps to do, I'm not going to round it yet. But I am going to remind myself that that's where I should have rounded it. This should be a 2-digit, 2 precision number. But I'm only keeping this for the calculation. That's why I wrote a 2 here. This really should be 2 significant figures. But I've left the extra and not rounded yet because I'm halfway through a calculation. All right, so I calculate that.
So the calculator, would you put .479?
Yes.
Okay.
Yes. That's what I mean by keeping this. I'm actually going to put it in the calculator. So I'm going to go 6.78 times 5.903 times 0.479. Calculator says that's what my calculator says for this overall calculation. I had 3, 4, and 2 for significant figures. So there's 2. So I'm actually not even going to be in the decimals for the answer on this one. The 1 does not round to 9. So the final answer here is 19. 19 point something would be wrong. 19 point something would be wrong. This is literally 19 if you follow the rules.
Because of the 2.
Because of this was 2. So this ended up needing to be 2. I have, at the end of this presentation, I'm not sure I'll get through all these slides today because we still got to take that ACS thing. But these last 2 slides with the slide 7 and 8, you see this says 39, 40, 41, 42. These pink ones, I've worked out the answers to. The ones on the left are copied out of the book because they gave the answers in the book. They're just buried in the appendix 3. But I put them here just so it's easier for us to see. This is the book. If you poked around on it, you know how to use the table of contents over here. So we're in this chapter, chapter E, the beginning. If you go down to the very last section, there's 3 sections at the end of these chapters. One of them says self-assessment, name of the chapter. One of them says chapter summary, name of the chapter. And one of them says exercises, name of the chapter. These are in exercises. You might find some in the self-assessment quiz thing. We haven't done all of this yet, but like this one. How many significant figures are in this number? 0.080320. How many significant figures are there?
6.
2, 3, 4. Anybody?
4. I'm gonna go 5.
It's 5. So So there's 2 leading zeros that aren't gonna count. This is number 3 in their self-assessment. Those 2 leading zeros don't count. The trailing 0 does count. So you have 5 digits. Anyway, you can find some of those in there, but the ones I wanna point you to are these. So this is for you to practice later, but we'll go through some of these now. Number 39 in that section. Start there. This one is just asking you which are significant and which are not. We already have pictures of that. 39. I'll write these on the board. So this is practice just looking at a number and deciding how many significant digits are displayed. So and yeah, there are units, but you can ignore these units when you're doing this for now. The units don't change anything I've described. Like this one is in kilometers, this one is meters, this one is seconds, this one is centimeters, but we'll get to units. So can you tell how many significant figures here? About this?
6.
1, 2, 3, 4, 5, 6, 7.
Oh,
7.
There's no leading zeros or trailing zeros, so this one should be easy. You just count all the digits you see there. How many significant digits here?
31,
2.
2,
It's gotta be 2.
Y'all are all over the place. These are leading zeros, so those don't count. It's 2. The trailing 0 does count. So all of these are significant. There's 2 here. How about this one? This one's 1. I probably didn't put the right number of zeros here because there's so many I didn't count. But this is only one significant figure. These are all leading zeros. All the way up to that 2. So there's only one significant figure there. How about this one? 4. This one's 4. Leading zeros don't count. We got 1, 2, 3, 4 trailing. So I have these for y'all to practice, and I've given you all the answers in here. Let's do some of the calculation ones. The book gives you some of the odd number ones, but I went ahead and copied it into that PowerPoint. Okay. 7. No, that's not one. This is A. So what's the first thing you want to do?
Find a
She
significant-
said cry.
Find a significant number.
count this.
Yes. You've got 3 input values here. You've got to calculate And the first thing you do is figure out how many significant figures each one of those has, because your answer has to be the one with the least. So how many here? 5. 5 there. How many here? 4.
4 again?
Yep. You follow? I did that quick, but there's no leading zeros. These have trailing zeros. We counted those. Any sandwich zeros, definitely. Yes. All right, so this means our answer needs to be 4. Now I get to use my calculator. Uh, 97.530 times 4.020 divided by 100.4. And my calculator says, I'm going to write down everything my calculator. 5, so 8, 5, 6, 5, 7. All right. Since I need this to be 4 significant figures, I'm going to underline those 4 digits. You with me? Then I'm going to look one more out to see if I want to round, but I'm not going to round. So the answer to this one is. I'm going to double check what I put in here. 3.9. I did something wrong. Was that 48? I did something wrong. 97.530, 4.020. I punched the wrong key or something. I'm pretty sure that's wrong. Anybody else calculate this?
It's because on there it says 100.04 and you wrote 100.4.
Yes, that's what it is. Let me do this correctly, just so it's not confusing later. Oh, and that's 5. That makes this 5. But we're still using 4 because of that. We're using the lowest number. This is why I double check. 97.530 times 4.020 divided by 100.04. Yeah. So this is correct. 3.9193. I'm keeping 4. So the 3 does not round to 9 up, so 91913. Still messing up, y'all. 1. Okay. So there's another example of a multiplication division. So there's more here that you guys can practice. Let's do addition subtraction.
Excuse me. When it comes to like the on the slides, a lot of like the stuff says like it gives like recommendations about the book and what the book says. Do we need to know that stuff? Like I know we talked about it earlier at the end, how like some books put the decimal at the end but don't put the following year behind, like stuff like that. Do we need to know that?
Yeah, that rule, it does show up enough that you need to know. All the other rules are standard.
And if the wording in the book or on the slides is confusing, we'll go over like breaking it down further in the exam sessions.
Yes, ma'am.
Yeah, this convention is what you're talking about. When there's zeros just to the left of the decimal, if these don't count, then you don't put a decimal there. If those do count as significant figures, you do put a decimal there. That's the only weird rule. But it's common enough that I think you should know it. I mean, it might show up on the test. Okay, let's do some addition subtraction. This is okay, so I'm adding these, so I'm using addition subtraction rule. What do you need to take note of here? This one goes 3 beyond the decimal. And this one goes 1, 2, 3, 4, 5 beyond the decimal. So we need to round this one back to 3. Let me do the math. So I will put in plus 0.09879. Calculator says and again, notice we're not really dealing in significant digits, we're dealing in what's after the decimal. So that's what my calculator says. I know that I need to keep the first 3 after the decimal, so that's what I'm rounding to. So my final answer is, and what goes here?
3.
It's a 3. I look at that next digit out, and it's a 7, so I do round this one up. And that's the correct answer. Addition, subtraction. So these are at the end of this PowerPoint. Okay. So the first slide was determining significant digits. The second slide is the mathematical rules. Stuff on scientific notation. It's in Appendix 1 in our book. I'll go to it.
Excuse me. I thought the leading zeros were insignificant. What made those?
This is the addition subtraction rule, and we're not dealing in significant figures. We're dealing in how many places beyond the decimal.
Okay.
This book is weird. All the appendices are in a tab called back matter. I've never heard that word anywhere in my life except for here. I don't know, they're just trying to be cute. But to find this appendix, Appendix 1, any of these appendices, there's all the way down at the bottom of this list under back matter. And the first thing in Appendix 1 is scientific notation. So I'll give you my description of scientific notation. I'm curious what it says. Okay. Here's something that textbooks never describe. Scientific notation means we have a number like and we represent that huge number by doing this as a power of 10. These two things equal each other. See if you agree with me. 10 to the 5 is the same as 10 to the 5. 1, 2, 3, 4. That's what 10 to the 5 means. I'm guessing you guys know that much. That 10 to the 5th power is 5 zeros. And if I take this number and multiply it by 10 to the 5, I get this original number. That's using scientific notation. But let me point something out. I don't want to do this. Let me get zeros out of the way. I want to do this. Okay. That number and You sort this or it's gonna take all day. All right, here's my point. All of these numbers 100% equal each other. Would you agree? Okay. Should have done. So these also, you can continue with this as far as you want to go. I can also do, let's do, those also equal these numbers. Do you agree? I'm just kind of taking it the other direction. 10 to the negative 10 means divide by 10, which would knock this 0 out. 10 to the 2 means divide by 100 instead of multiply by 100, which will knock these 2 out. So I could continue and do the negative numbers, negative 3, negative 4, negative 5, and keep adding zeros there. You see what I've done there? So even those on the right there equal all of these. Once you do the math with the power of 10, they all end up equaling exactly this. Do you know what 10 to the 0 power equals? It's 1. I think it's true that anything to the 0 power equals 1. It's a weird rule, but it's true. But so that's why this number, you're basically multiplying by 1, so that's why I was pointing at this number, saying this is the actual number we're talking about. But it's using scientific notation. All right, here's the point I want to make. I can already tell this book doesn't make this point. Scientific notation. Everything you see over here is in scientific notation. Those of you who have learned about scientific notation, is it anything about that bugging you when I say all of those are in scientific notation? Okay, good. All of them are in scientific notation. And it doesn't bother any of you? This one doesn't seem special to you somehow?
Yes.
Okay, that's what I'm getting at. These are all in scientific notation. But this one is in standard scientific notation. There's only one on the board that is in standard scientific notation. Standard scientific notation means out of your infinite choices, because this really is infinite. I could go 10 to the 7, 10 to the 8, keep going, or I could go 10 to the negative 2, 10 to the negative 3, and as long as I keep changing this number accordingly, there's an infinite number of ways to represent any number in scientific notation. But there's only one way to represent it in standard scientific notation.
Why are they both to the power of 4?
Oh, I messed up.
Oh.
1, 2, 3, 4. 1, 2, 3, yeah. Thank you. I don't like having mistakes confusing you. Is that right now?
Yes.
I did that kind of fast.
What makes it in standard?
You might have something. By convention, it's just a standard we use. You always put the decimal just to the right of the first digit. So whichever one of these powers does that, that's the one that puts it in standard scientific notation. And I'll show you kind of how you get there. Let's keep this number. Oh, so I always like to pick on textbooks wherever I can. Because textbooks are terrible about this. Instructors are terrible about this. I'll do it sometimes. I'll say, put your answer in scientific notation. What I mean is standard scientific notation. And that's what anybody else means when they say it. They just are forgetting to say standard. So if you see a question somewhere that says, put your answer in scientific notation, they do mean standard scientific notation. All right, so let's say you had this number, and your instructor said, put that in standard scientific notation. First of all, so the decimal is essentially here, and you want it here, and you just do this, you count 1, 2, 3, 4, 5. It's 5. And you'll go 3.44143 times 10 to the, it's not really to the 5 though, because oh yeah, it is. This one is to the 4. So I moved the decimal back 5 times. That's why I have to multiply it by 10 to the 5, so it will continue to equal that original number. I mean, we can't just move the decimal and make it a completely different magnitude number. It doesn't represent what it originally was supposed to represent. This number and what this represents are 100% equal to each other. We're just expressing it as a power of 10. So you get the standard scientific notation. Let me get throw another example at you. What if it was this? What if it was that? I said, okay, put that in standard scientific notation. You want the decimal here, so you go 1, 2. Now those two numbers equal each other, but this is in the standard notation. And let's do one of these that are, okay, how do you put that in standard scientific notation? Now we're moving a decimal the other way. 1, 2, 3, 4. So 3.416 times 10 to the negative. This number and what this represents equal the same thing exactly 100%. So that's how you do standard scientific notation. Let me take it a little further. If you had that, and somebody said, put that in standard scientific notation, you would do this. 1, 2, so we have to multiply by 10 to the 2. But I had this was originally attached to. The powers of 10 can show up for other reasons other than someone asking you to put it in scientific notation. They can show up other ways. So if this was already there and somebody said, put it in standard scientific notation, you would get this to represent this number. And you just go times 10 to the 4. And then you combine the two powers of 10. Times 10 to the 4 plus 6 times 10 to the 6. So this number and this number and this number are all exactly the same. Whatever that comes out to be, whatever that comes out to be, whatever that comes out to be, they're going to be able to be exactly the same. And I did this with the standard way you add exponents when you're multiplying. You guys understand that? You understand how I got a 10 to the 6 from a 10 to the 2 and a 10 to the 4? I just combined them into one. So this number put in scientific notation is this. Make sense? Standard scientific notation. Let me show you one other thing. So I put in this PowerPoint some practice problems. I don't have anything on scientific notation there. I need to get some more stuff built. But look at this in our course. Under coursework, if you go down to quizzes, I've made some short quizzes that are for practice. Sig figs, calculations with sig figs, and this one's scientific notation. I think there's only 3 questions in here. This is not for a grade. You can go back and do these as many times as you want. Just throw some. Let's see if it's set up where you can read them. Yeah. So if you click through, I just threw answers down. I happen to get one right. You can come to this at the end and see which ones you got right and which ones you got wrong. Truthfully, you need a lot more of these to practice, just so you have a bunch of them to go through. Lucy, do you have any resources where you could build questions like that? Look at those. You might be able to add things in there in D2L.
For this, that's what I'm working on for my session right now. I think, okay. I honestly find AI super helpful for things like this. You can plug in one practice, like let's say he posts a practice problem, and you're like, okay, like I don't know how to do this, like I need more like this to practice. You can plug it in and be like, please make 10 more practice problems.
That's what we want. Yeah, that's exactly what I need to learn to use these IA.
And so like I did that nonstop for calculus. Calculus is still really hard, but it was helpful to like figure out the same kinds of problems with just different numbers, because it's like really repetition with this kind of stuff. So
yeah, so like this one has 3 problems in it. I wish I had 1,000. So you could just do as many as you want till you went, okay, I think I understand this. You know what I mean? Because that's really what you want. You want these drills that you can go through.
yeah, that's the most helpful thing I think.
But do start looking at these. We'll get more. We have that ACS test, but I think they have time to do a little more.
Is it always?
Oh yeah, look at this. I can probably make a link that's over here in this area. But for now, you go to coursework and you go down to quizzes. Coursework, quizzes, and then you'll see these things. I want to do a little more.
So what I do is start conversion.
Yeah, I'm thinking we can start with
Or like SI units.
SI units and conversions. That's where we can go next. I don't have anything for them for practice.
You just want to
So I'm thinking maybe I'll just wait until the ACS test. Because I like to introduce practice problems as a new thing, since I don't have any of that stuff ready. But you guys can look at this PowerPoint and see what's coming out. This slide is just introducing the SI units, the units we use in science. I covered up in my PowerPoint. We're not really going to use, all these slides are right out of the book. I just copied the figures that are in the book. We're not going to use electric current, luminosity. But volume is a derived unit, so they don't put it in this list, but I wish they would, because these are the ones we use. We're going to mostly use length and mass. Temperature ends up being kind of an easy thing to deal with. We'll definitely use the mole, but that comes up later. It's just this definition of volume. 1 centimeter cubed equals 1 milliliter is going to be useful for when we do these. This next slide, these at the top were in an appendix in the back of the book. This was in our chapter, so I just put them both here. Realize, I will give you that on a test. I will give you all of that on a test. Slide 4 and 5. I'll even give you that on a test. You don't have to memorize. I lean away from memorizing. I just want you to be able to work with these things. Memorizing to me is not what I'm here to do. I don't have to teach people. So know that. And I will get to, we don't meet again until next week. Yeah, I'll wait till Monday. But I'll start going over these units and little bits of math called unit conversions will start. I'll probably put density in here too. But yeah, let's just take the ACS test, and then I'll have more problems with them.
Do you want to pass these up?
Yeah, pass out. So, this ACS test that you're about to take, I don't expect you to do well. You get total 0, 1. I think it's silly. Everybody sign up. I'm going to put the signage over here. Don't forget to sign. So if you've taken chemistry before and you want to do your best on this test, that's fine. Just realize. I've got an extra pencil.
Yeah.